In this lesson, we are going to introduce this idea of a definite integral. A definite integral is a Riemann sums will only be an approximation of the area under the curve. So if we kind of go back to this visual real quick, that if we are doing a Riemann sum, which basically means we're creating all these little rectangles and adding these areas together, and these heights of the rectangles are based on points on the graph, gives us a little bit of accuracy. But we're going to definitely be off. It's never going to be perfect because we're going to have pieces that are extra or pieces that are missing. And so that becomes a bit of a problem. And so if we want to get more accurate, we can make more rectangles and make the widths smaller, right? And we can make it, and so we have almost an infinite amount of rectangles, but that makes our width of our rectangles infinitely small. So that's where some math kicks in. And so they're going to be approximation of the area under the curve unless you make an infinite number of rectangles with an infinitely small width. So to do that, you start to add all these things together. This look is an integral. And we're going to be going, it's going to be defined from A to B. And it actually becomes an integral is a sum because we're doing a sum of an infinite amount. And so here are all the little pieces to it. So this f of x is going to be your heights. And so that would be us kind of finding all these different heights. But then when you find a height, then you're going to need to multiply it by a width. That's going to find you your area of your rectangle. The width is going to be this delta x. So the delta x is the change, basically. And so, if you have a million rectangles, you're going to take from 0 to 3 and divide it by a million. That's going to give you little teeny tiny widths. And so you're going to find heights times widths. So what if that width becomes infinitely small? And you're going to add all these values together, all these little rectangles together. It basically turns into an integral. So an integral is finding the area under a curve and as exact as we can possibly become. And so we have this setup that we have a lower limit. So you're going to go from this value to this value. And we're going to do the antiderivative. And then eventually we're going to show you how to plug these values in and actually find this area. But it really stems from the width of these rectangles, basically creating an infinite amount of rectangles with an infinitely small width. And so it becomes a limit problem, a limit attached to a sum. All right, so this video is not going to do the math quite yet. All we're going to do is to practice kind of rewriting. All right, so taking a sum and say, well, what did that look like? How do I rewrite it as an integral so I can actually do the math to it? And so to rewrite this, this is your lower bound and your upper bound. And so this is your A, this is your B, and these are the pieces of your equation. So your X on here and your X on here, that's just your, we're going to do from 0 to 2. It's basically just 3x squared minus 5x plus 4. All right, so it looks very straightforward. And then times dx. So that is kind of your width, but your width is becoming infinitely small. And so that's kind of how these pieces are. So that change in x becomes your dx. This little x star k is just an x. So it's 3x squared minus a 5x. And so this, we're going to take this one, and anywhere you see, if you need to, right, there's your x. There's your x. So I'm going to do this one. I'm looking at from 1 to 2. Finding the area under the curve, and this is an x, and that's an x, and that's a dx. So we have x times natural log of x dx. And so the next video is we'll start talking about how do we actually figure this stuff out. And we're going to start by being able to have things that, because we're not going to have the math quite yet, so we're going to look at kind of the geometric version of these things.